Thank you very much again, for nice introduction, and I'm so happy to be involved to this presentation, which is we focus on the biochar, which is my main ongoing research in the last many years. Today I will focus on the talk about graphite, making from the biomass, of course, and for green process industry, that is for the applications for the iron and steel making and the batteries. I will start with simply what is graphite, what's demanding, how it's produced today, and what we are going to do to convert the carbon materials from biomass to the graphite. And of course, not only one step, it will be involved which kind of feedstock, how we will control the parameters, and finally we have to do the purification. And the key issue of this technology is how to scale it up. That is reactor, and I will stop in this shortly summarize. You can stop me if I have any time problems or other questions. Just stop me.
Yes, please. You have around 30 minutes.
Good. So, what is graphite? Of course, we understand very well. You can see what is. Let me see the point. So normally you have the charcoal or biomass. The structure is quite not very well organized, and like this kind of form. And what we maybe talk about graphite, then you have much very good crystal. In principle, we can say it's very high, very good crystallization. Then you have different properties like the no thermal expansion, thermal shocking, resistant, and especially very high electrical conductivity and thermal conductivity. That is the main application for the industries. So when we talk about graphite, when we talk about the parameters, what are the important parameters? In principle, we talk about the three parameters. One is the D002. That means the layer between the graphite. How far away from this distance? Of course, if there's only one layer, that is graphene. If it's less than 3 or 4 layers, that we call that as a 3D graphene. If I have more than 10 layers, that's graphite. Another parameter is LA, that means the distance, how large of the graphite you can have, and also which layers, that's LC. So LC, LA, and D, that's 3 parameters to decide the quality and what we need for different applications. Of course, you have some kind of physical properties, for example, like the particle size distributions, defects, depends. For example, defects, that means sometimes defects is very good for the batteries, like the electrical chemical applications, but the defects will be very bad for the conductivity of electricity and the thermal conductivity. That's different. Here, that's the main. When we talk about the quality of graphite, that is what we have to achieve. Demanding of the graphite. Basically, the 2 big applications. In principle, graphite is used for the whole life, almost everywhere. And the 2 big applications. Another one is the electrodes. For example, like the iron and steel plant. When you have the electrical arc furnace, you need a very big graphite electrodes. More than half of the materials used for the iron and steel making. Another one is new applications. That is the lithium batteries, which is today is more than over 14, and this will be increased as well. Of course, the graphite almost used in other applications like lubricants, calcium powders, reflective materials, and also a lot of aviation, aerospace, automotive, nuclear, energy storage, military. Now today, if you saw the news, might be used for the moons for the energy storage as well. Quite widely applications. And so some example, let's say go to for some kind of academic numbers. You can see for the graphite in the steel plant, like the electric arc furnace, 1 ton of the steel making, you need about 1.7 kilograms to 3 kilograms, depends on the how much of the facility. Then when you talk about 1 billion tons of the steel making, then you can think about how much is graphite do we need. Another big application is graphite needed for the aluminum. In the primary aluminum production, basically it comes from electrolytes to make the purification of the aluminum. That's quite a lot. You need about 300 to 450 kilograms per ton of the aluminum. Then you can think about this another quite big carbon emissions, which is so far there's no other way to reduce this one. More hottest applications is the car. Let's say take example like the electrical vehicle, like the Tesla and the new model, almost 100 kilowatt of the Tesla. You need about 100 kilograms of the graphite, depends on the companies. That's so one car you need about 80 to 100 kilograms of graphite in your car. Now you can imagine how much graphite do we need. Also, it's quite a lot of graphite used for the fuel cells. It can be used for the batteries, storage energies. That's the main new challenges we have to face. So we know graphite is so important that what is produced today? Today, mainly comes from two ways. Natural graphite. One is either from the mountains, you dig into the graphite, or you make the synthetic graphite. Let's start from review what is happening from natural graphite. It's basically, you go to the mountains, you have the graphite minings, take out of the rocks, make the mechanical separations, and finally, concentration of the graphite, take rid of the stones and other impurities. Finally, make the downstream process, remove other impurities, get the graphite. Either you go for the some applications, or you go to the battery grade applications. In any way, you have to do some post-treatment. That is mainly, let's say, natural graphite production, which is happened in the last 200 years. Another one is the synthetic graphite. Of course, natural graphite is limited locations and also limited of the graphization as properties as well. So therefore, there another kind of technology which comes from the synthetic graphite. Today, most of the car batteries applications come from the synthetic graphite. So the process started from coal tar pitch, which is phosphate-based, and after this coal tar pitch mixed with coke, then we go to the caramelization at a very, very high temperature. Basically, you have the pre-baking at this up to 1,200 degrees. You do the caramelization. If you stop here, that is aluminum. This carbon can be go to for the aluminum primary production applications, but it's not good enough for the battery applications. If we want to go further for the battery applications, high quality and high caramelization of the graphite, you would go further to treatment to do the next step, caramelization. Started increase the temperature to 2,800 degrees up to 3,000 degrees. And in principle, you have to hold this temperature for more than 3 days or 1 week. So finally, you will get graphite for different applications, either for electrodes, fuel cells, or batteries. So you can see today's synthetic graphite production have two main challenges. One is phosphate. You have to come from this coal tar pitch or coal. Secondly, it's energy intensity, very, very long time and very, very high temperature. That is a challenge. But unfortunately, today, most of the graphite production for batteries come from this process. So, what we can do? We have the biochar, we have the biocarbon. So what we have? We have this biochar from the sawdust or from the agricultural wastes. In principle, it cannot convert to the graphite directly. What we need to do is we need a catalyst. In principle, the catalyst is a kind of metals or metal alloys, for example, like nickel, iron, molecular, then put in the high temperature, then you can get the graphite. You can force the structure of the biochar from the moves full phase to the qualification was very, very well crystal. So in this talk, I will talk about the mechanism process, which kind of carbon precursors, catalyst, and how to do the purification, reactors, and some applications. So in principle, you can see what we need is a mixture of the char and the catalyst to make it graphite. What is kind of mechanism behind? In principle, there are two kind of mechanisms people agreed. The first one, we talk about the dissonation and the precipitation mechanisms. That means we have the biochar, we have the metals. Biochar will come inside dissolution into the iron and these metals. Then after a certain time, the carbon will be precipitate. Then you get the graphite. That is one idea. Another way is say, okay, maybe it's not directly in this way. When the carbon comes into metals, maybe something happen. So people say might be carbon come to the liquids, come to the iron metals, you will formate in the carbonites. Iron carbonites, after certain time, the carbon will be precipitation again to formate on the surface of the iron. That's another mechanism. In principle, basically, the two mechanisms are not so big a difference. Idea is the carbon coming to the catalyst after a certain time, it will go outside. So when we design new mechanisms, when we design the process, then in principle we have to understand how fast will be carbon coming into the steel, come to the iron, and in which condition you will come to the iron. Secondly, when we want to get carbon outside of the steel, the iron, what is the speed, how fast, and in which condition? So that's two key parameters which is still not so clear, and a lot of knowledge we should go further as well. In principle, if we go to the engineering applications, there are two different ways to make the graphite. And ideally, in the beginning, we have the biomass. We do the pre-treatment. Basically, you can try to remove a lot of hydrocarbons. You can also put your catalyst in this stage. The pre-treatment can be the hydrothermal caramelizations, fermentations, or other kind of pre-treatments. After the pre-treatment, then you do the graphitization or heat treatment again. Then, of course, this is normally temperature either 800 degrees to 1200 degrees. Of course, because you come from a raw biomass, you will have a lot of bioweapons have been released. It will depend on the catalyst. If the catalyst come from the iron source, then you, of course you have a lot of chlorine environmental issue have been released. Then heat treatments for the catalytic graphitization, what we need is high temperature in certain time. In principle, different way to heat up the process are okay. You can come from the resistant microwaves, induction, geoheating, or even modern steel. Which one you can go further depends on your know-how and the different knowledges behind of this one. After the heat treatment at 1,000 degrees, the next step is purification, the separated the catalyst and the biochar. Then you get graphite and some other impurities. This is one way. So when in this way, you can see if we start from the biomass, in the biomass, we know this fixed carbon is just 20%, and the graphite is 100% of the carbon. That means you have 80% of the bypass materials have been treated away. So therefore, recently people think about let's don't start from the biomass. Let's start from biochar after the pyrolysis. Then here you can get 80, 90 or 95% of the carbon, fixed carbon from the raw materials. Then you mix with catalyst, you do the heat treatment, then you do purification. So this one is quite a lot. In this way, you can see the whole process will be much simpler and it will be much more efficient. At least you don't need to treat 80% of the biomass materials. So in principle, today, most of the startups, new companies started from the biochar. They do not start from biomass. So of course, the knowledge is not just come from heaven, suddenly come from today. In principle, we can see from the idea get the globalization of graphite production from biomass started from beginning of the 21st century. This is 2008, something like that. People started from the hydrothermal carbonization based technologies. That's the main step. And up to the 5-10 years later, people think about because if you go to the HTC, high thermal carbonization, it's quite a longer process, also batch type, high pressure. Then why can be tried from direct biomass-based researches? And today, almost people focus on the biochar-based. That is, if you talk about the globalization process, development, just few of them. But of course, just still some people work on their HTC, hydrothermal carbonization, but no one really work on the direct biomass-based globalization productions. Because of the demanding of the graphite so much, then you can see the publications. In principle, publication of the globalization of the biomass is increased quite a lot. Main topic come from the material science and energy fields. So let's say when we have to make the graphite, what is the materials we are talking about? In principle, here I would like to separate the carbon precursors as two kinds of materials: hard carbon and soft carbon. We will not talk about the woody-based biomass or agriculture-based biomass or whatever. Let's say start in this way: hard carbon and soft carbon. You simply say what is soft carbon, like the coal tar pitch, nickel coal. You can derive the graphite carbon. When you increase the temperature. That is people use today for the synthetic graphite. Unfortunately, most of the soft carbon is a phosphate-based. And we have quite a lot of biomass-based carbons, which we talk about, like then unfortunately is a hard carbon, or you can say is a non-globalization carbons. In principle, say in this way, once you increase the temperature up to 3,000 or 4,000 degrees, you only get hard carbon. You will never get graphite. Of course, hard carbon have another applications, but it's not for the graphite applications. So, of course, another materials, for example, like bio oil, that is blending together, that is hard carbon and soft carbon mixed together. So, what is hard carbon? In principle, all the most 99% of the biomass-based materials, like we talk about sawdust, bamboo, coconut shells, agricultural waste, straw, that is come from the hard carbon. And the soft carbon basically is the phosphate-based carbon synthetic polymers. And our main topic, our main challenge will be the hard carbon, which is we always talk about very widely available and force-free. So the second one, we will have the carbon precursor, then we have to go for the catalyst, which is the key issue, another key issue to make the globalization. Today, most have been used, the catalyst can be the metal-based metal salts, like the basically is chlorine, iron, chlorine, nickel, and so on. And also people also tried for the pure metals, like the iron, aluminum, copper, or molecules. Then you can see the difference. If we have the pure metals, then you don't have the environmental problems. You can never release C chlorines, NO2,3s. But also you have another challenge as well. Metals oxidized is also quite widely used. Is between the environmental problems and the materials as well. And of course, if you say one pure metals is not good enough, we can also try the alloys. Basically, today 2 or 3 kind of alloys have been tried. Of course, you can also try the high entropy alloys. That is, no one have done yet is in our plan. And also, when we talk about the catalyst, which is micro-based, of course, the best way you can also think about other way, for example, non-micro catalyst, but not so much you have to try. The two reasons: one is very high cost, secondly is the process needs investigation. It will be need more time to do this one. So when we have the catalyst and carbon together, then the next step, how we can mix with catalyst and the carbon together, in principle, depends which kind of technology, depends which kind of catalyst you can use. You have 3-4 ways. First one is the weight implications. That is, you have the put the liquids together with metal salts and the carbon precursors. You mix together, stirring for many times, then store it there for 1 week, 1 day or 2 days. That is weight implications. And if you can also have the dry mixing. For example, if you have the pure metals, then you don't. It's very hard to get the weight implications. You can make the dry metals, make it by the ball mill, for example, mix with the carbon and the metals. And also you can do the simply way, just go to the pellets on the liquids. Then you cast in the carbon precursors and this catalyst as the pellets or liquids, depends which process you can use. And also, let's say if we have make a very good technologies, maybe we can use a modern iron process. We get a very high temperature, more than they make the iron in the molten phases. Then you put this, carbon in. Then you can stir carbon in the molten liquids. Then you can another applications. Also depends very much which kind of process you can use. It's not so easy to say which technology is good and which process is it depends which kind of catalyst you want to use, which kind of process you want to use. You have always have some good points and limits. For example, for the weight implications, it's very good catalyst. It's very easy to simplification and scalable, but your limitations, typically you cannot use the metal powders. And if you go for dry mixture, basically you have to use metal powders, and its catalyst distribution will be not good enough. The pellets of liquids, it's very good. Can be used for very special reactors, very special process, and in principle, not so easy to make the scaling up in the big industry later on. Modern iron steel, it's very high catalyst efficiency and very fast, don't really require the premixing. Let's have a very big potential for large scale applications in the future. But of course, modern steel, modern iron, with the high temperatures, energy intensive process compared to others. So after we have the catalyst mix with biocarbon, then we put in the furnace. It depends on the temperature, depends on the time, depends on how much ratio of catalyst and the carbon. Then you will get a different degree of the of catalyst. In principle, if you have very a lot of catalyst, a lot of loading catalyst, much more catalyst than the carbon with very high temperature, long over than 1,300 degrees, then you will get a very good graphite. You can get also polarization up to 99%. Sometimes it's even better than the normally synthetic graphite. Or in another way, if we have very short low temperature from 800 degrees, very low catalyst ratio of the biomass to catalyst, then you will get a partially polarization. You still get some graphite, but it's still almost phase graphite. Of course, then depends on the temperature ratio and the time. You get a different type of the graphite, then you have different applications. If you target for the battery applications and steel iron making, then you have to come to here. If you come to other applications, lubricants, reflective materials, then maybe you can go stop in here, or even come to the other, depends very much applications, which means in principle to say, when we have the catalyst and the temperature over than 800 degrees, the most fluorocarbon start to convert to the crystallization and the graphite. And the complete graphitization, you will need more time and more temperature and more catalyst. So after we get the catalyst from the materials, the next step is how to get the catalyst out of the graphite out of the catalyst. Then we come to the purification process. In purification is very, very important for the final applications. In general, we have two ways to do the purification: chemical methods or physical methods. Chemical methods, basically you use the acids or acid-based leaching chlorine. Of course, you can also do the fermentations, some treatment that's quite widely used in the real industries. If we go further to see the purification, first one is physical purification, flotations. Basically, you just put your fixed materials into the reactor, you stir it, then the materials will separating by the density. That is also graphite is hydrophobic, then you can easily to separating. And of course, the liquids can be the water or some kind of special salts in order to separate the hydrophobic, and it depends very much. And the good issue is this technology is almost available today, widely used for the mining industries. You can also use one for separation in our process. Of course, if you don't want to, if you cannot do the full work by the flotations, then ash leaching can be another way. Depends what you have in the materials. For example, you have silicon oxidized, then you can separate it by the hydrofluorides. Basically, this is a chemical methods to remove impurities. And the commonly used material liquids is hydrofluoric acids. And of course, you can very good to remove the silicon oxidized, but the hydrofluoric acid, we know it's quite environmental pollutants, but it's still widely used for the other industries as well. And sometimes we have impurity quite a lot. It's not only have the silicon oxidized, we have the metals, we have the other acid compositions. Then we have to use the more multi-stages, like the acid-based leachings. You can remove the impurities. Basically, we were combining the HCl, H2SO, and alkaline acids and alkaline together. We can remove the metallic elements in the graphite, use acids, and then after that one, we use alkaline to remove the silicon impurities. In principle, that's the way. Also, there are quite a lot of available work similar to the mining industry to do this kind of jobs. It's useful for us as well. Another one is a very, very hot topic is, let's say, the thermal purifications. It means whatever you have the impurities, if the boiling point normally is belong to the 300 degrees, if I can heat up the materials up to 300 degrees, most of the impurities, like the metals, will be vapor into the gas phases. Then you will only get the graphite. It's here when this temperature, vaporization temperatures, you can see the highest metal vaporization temperature is legal. It's about 2,913 degrees. If you go to for the 3,000 degrees, you can almost remove all the vapors. It's quite widely used, but the challenge is how to make the efficient furnace on this kind of thermal purification is still also very good topic to go on as well. Purifications, Another one, in order to reduce the metals in the materials, very big applications is chlorine. Colonization is widely used for the purification process. In principle, we mix with materials with chlorine. Your colonization of the metals, then you can reduce the temperature for the. Then you can make this as a water solution. Then you can easily remove the chlorine. So it's quite widely, for example, used like the iron is a low temperature, 500 degrees is more efficient, but the nickel you have to go to the high temperature. Unfortunately, for the purification, get a high quality graphite for battery applications, we always need the multi-stages to combine together. Also, we need all the technology here. As I said, it's quite tough to say which one is good, which one is bad. It depends on which materials do you have, which process you prefer. Now you can see the chemical metals. Basically, you have the leaching, acid-based leaching, colonization. Basically, you can get the 1999% of the carbon, and most of them are quite good. Used the limits basically is the hazardous materials either from the chemicals or the colonization, collusion of the chlorine for set up gases, toxins. Basically, the environmental problems, and we have to be careful on this one. When we come to the thermal purifications, the physical metals, either flotations, you can have very big limitations. You can only as a primary purification, you can look as a final state, which is not enough. It's very cheap, but it's not so efficient. You can as a primary first step. And if you go for the thermal treatment, then you can get a very high, ultra high purification, even the energy intensive, but also the main challenge is the furnace, the reactor, how to design a high temperature reactor in the larger scale. That is a challenge as well. That is for the purification. So now, as I said, how we can make the catalytic polarization in the high temperature, we have already understand after mix with biochar and the catalyst, we need the catalytic thermal treatment that is a temperature over than 800 degrees, at least could all prefer as 1,500 degrees. You have a different way to go. In principle, today, when we talk of the force-free, no one field work use a force-based reactor. Always we only use electric heating reactor. Depends on the way how to get the electric heating. You have the heat resistant, microwavers, induction, geoheating, and molten steel. Heat resistant furnace, it's very simple. You can see you have to put the materials into the furnace. The whole furnace is heated by the resistant, like the morpho furnace. The temperature maximum highest goes for 1,800 degrees, start from 800 degrees, 900 degrees. It's suitable for the scaling up, quite very good. And the only issue is the maximum temperature is limited and energy efficiency is not so high. But this kind of electric resistance heating is quite widely used for most of all the life industry as well. Another hot or flash topic is that's a flash heating or geoheating, which means we make the pellets, we make the bed of the carbon materials. You use it itself, materials itself as a catalyst, as a heat resistant. Then you put the negative electrical carbon in, then you heat up. That is the geoheating furnaces. It's quite funny today. Geoheating or flash heating is quite hot for other applications like the waste treatment and chemical productions. But the geoheating actually it was started to use for the industrial applications in the end of the 19th centuries. The first applications is for the graphite production. All is silicon production, graphite production. Even today, the synthetic graphite production are still uses geoheating. But of course, today you have new ideas. You can try to make them better. Geoheating is quite faster, very efficient, and very high temperature can be achieved. But of course, the difference is you need the materials itself have some heat conductivities. And microwave is also quite widely used for the different people. Also, people say you're not heating by electricity. You can also get the influence by the microwave, so that is in fact your materials. At least people claim this, but in fact the microwave influence in the so high temperature it should be very, very small. But anyway, they can provide a very high energy, high temperature up to 1600 degrees to 1700 degrees quite faster. And the one challenge is very hard to make scanning up because of the microwave, how we can make the microwave in the big scale. That's the kind of challenges. But anyway, from the laboratory research perspective, there are quite a lot of research groups believe or trust microwave is one of the best technology for the globalization. Laser furnace, another big state of the art is they say you have today you have the carbon materials, you have the laser, the higher energy intensity, maybe I can force the carbon from the most of the carbon to the graphite, crystal carbon, and they claim they did this one, they claim it works, but not so many work have been done in this way. The challenge, the good issue is the laser furnace can go to very, very high temperature, and also the challenge is how to make scanning up for the real industries. Another industrial applications which typically used for the today's iron steel making and metallurgical applications, so that we have the induction furnace. Induction it's quite advanced furnace. Is heating by the electrical induction, and you can go for very high temperature up to 2500 degrees. You can heat up very fast and very easy scaling up, because there are a lot of real applications for the induction furnace. It's quite a good candidate for our process to the next step. Let's put everything together. We have the electric heating, resistant heating, geoheating, microwave heating, laser, and induction furnace. Basically, heat resistance furnace is widely used for the today's industries. It's slow heating, very possible for the scaling up, but the temperature and the efficiency is low, both are low. And other technologies can be heated up very faster, and some of them have the very good scaling up, some of them have limits. It depends, and also in there are two different ways, like microwave, laser. People say they might be not only good for the heat treatment, but also used for the improve the property of the graphite. But in general, we can say what we need is heat treatment. We need is temperature. Temperature is more than other, in fact, either for the microwave or it's lasers. If we have enough temperature, up to 1800 degrees, even higher, you will for sure get high quality. Other influence, like the microwave and laser, the influence should be very, very limited. Now we will come to the applications. There are quite a lot of applications. I will not talk about most of all of them. We will focus on two. One electrodes, that is iron steel making, and another one is lithium batteries. As I said in the beginning, more than half of the graphite today is used for the electrodes in the steel making. And in the steel making, we will need 10 billion tons of the steel production. Even today, the demand of the graphite will be even more, because the blast furnace is shut down, and most of the raw materials come from the raw steel, come from electric arc furnace. That's why we need the more electrical electrodes. Another one is lithium batteries. For different applications, the demand are slightly different. Basically, we can say, as I said in the beginning, the layer space, crystallization defects, conductivity, mechanical stables are different, demand are different. You have basically for the different applications, you have to do some post-treatment after we get the graphite from the process. We can see at my group, we have used for lithium battery testing with say half cell, full cell, and a lot of applications have been done. That is electrical chemical performance, and you can see we can achieve the specific Columbia specific capacity up to very high, basically over than 400 milliampere per grams of the graphite, and this is almost achieve the theoretical numbers as the today's synthetic graphite which you are able to achieve. And also Columbia efficiency is 95, 98. It's very good. It's good enough for the compared to the commercial available graphite. Of course, full cells testing will be need to be the more challenges. You have to change the capacity, more time, how long different voltages. Still, in general, say, we can say in this way, the quality of the biographite produced from our process is good enough compared to the available commercial graphite for the battery applications. Another application is graphite for the electrical arc furnace. For the electrical arc furnace, this is the graphite in the real plan. What we need, you can see when the electrical current passes through the graphite, then graphite is consumed. You generate an arc that becomes the heating. So what we need to understand is, firstly, what is the current performance, what is the electrical resistance in this graphite, and how much is graphite consuming per ton of the hot metals. That's not only for the iron and steel, also for the aluminum, for the copper production, do the same. We did the testing in the laboratory at KTH in similar way. Here you formate a graphite produced by ourselves, then you use the metals, then we try to use this casting metals to see how much you can use and to use it.